All right, so we talked about some three-phase sources. Now we're going to talk quickly about three-phase loads, and then we'll get into showing the possible configurations that we may have, which are probably pretty straightforward. There's only 4 of them. I talked about them a little bit briefly already. And then we will be solving some example problems, okay? So here we show, sorry, I didn't mean to bring that up. Here we show 2 different types of three-phase loads. We talked about how there were 2 different types of three-phase sources. Of course, there was the Y-connected source. Oops, I don't know why I'm on the thickest pen setting here. Y-connected source. And then, of course, there was the delta-connected source, which we saw is really just the Y-connected source, but we're using the voltages differently. As far as the Y and delta connected loads, it's basically just 2 different ways to connect 3 different loads. They don't have to be resistors, of course. They could be any number of elements that create some kind of impedance here, Z1, Z2, and Z3. But if they're configured in this Y configuration, of course, that's called a Y-connected load. And basically what it means for it to be Y-connected is it has a line to neutral voltage across it. So if you remember, we talked about line to neutral voltages a couple slides ago. This load Z1 has a voltage across it. It's going to be VAN across my load there. I'm going to have VBN across Z2. And then Z3 is going to have a voltage VCN across it. I guess I'll stay consistent with my colors again. Let me make this one red and this one green. And I'll also move this one a little bit closer to the load itself. And so you notice that these 3 loads, they have different voltages across them. And it's important to note the voltages that they have across them because we're going to be interested in finding the currents through these loads and how much power they consume on average and all the good stuff we've learned already, but it's going to apply to these 3-phase circuits, okay? And so what about the delta-connected load? Well, delta-connected loads don't have line-to-line voltage or line-to-neutral voltages across them. So let's just say line-to-neutral voltages, right, are connected across our Y to Y or our Y connected load. And then here we have the delta connected load, which has, so across ZC, what voltage do I get? Let me go to my off blue here. I get VAB across this load. For the A impedance, ZA, I get VBC, which I was drawing with this color, VBC. And then the final one, I have VCA across it. So we can see that the delta connected load has line to line voltages across the loads, and the Y connected load has line to neutral voltages across it. Now, there are 4 different configurations, so ultimately I don't want to make any super general statements, but I do want to just point out that the 2 different types of loads, just similarly to what I was trying to point out with the 2 different types of sources producing different voltages, the 2 different types of loads basically have different types of voltages across the load, and that influences the current that's going to flow through each of these loads. And so that it really is just important to analyze the circuit. I'm doing all this again just as prerequisite knowledge, so that when we get to see the circuits, nothing looks crazy and nothing is surprising. But at the end of the day, it's still just going to be figuring out what the voltage is across our load element and what's the current flowing through that element, what's the current flowing in the line, etc., etc. Okay, and so we're going to talk about line currents really quickly. When we're talking about line currents, we're always talking about the currents in the lines, and so that should make sense. So IA, IB, and IC, those would be my line currents for the Y-connected load, and similarly for the delta-connected load, it's the actual current that's in the line associated with it. So if I'm talking about line C, the line current is IC, which is the current flowing in this line. IB, this line. And then you see that KCL is going to apply, and we're going to get that current to split between ZC and ZA. Same goes for IA. It's going to come to this node and split between ZC and ZB, where for a Y-connected load, the line current goes right into the load that it's connected to. And then they all flow back on the neutral channel, or on the neutral line, okay? And so that's the line currents. I'll draw those in red, and I'll draw the phase currents in a different color. How about orange? The phase currents are the currents through the actual loads, or the actual impedances. And so for the Y-connected load, it should be pretty easy to see that the line currents are actually equal to the phase currents, but that is not the case for the delta connected load. So the delta connected load, ZC is going to have a current that flows through it, right? And that's not going to be the same as this current here. This current is going to come into this node and basically split between these two paths. And so part of it's going to flow in ZC, and the rest of it's going to flow in ZB. The same goes for the other two currents. So I might define my currents like this. And so again, we can see that ZC is going to, or that current, that line current IC is going to come and flow into this node, and it's going to split between ZB and ZA, or better yet, I drew ZA this way. And so again, it doesn't matter how we define our currents. We can define them however we want. If we find out that they're negative, we can say that we define them backwards and all that stuff that we learned in 220. I just wanted to make the distinction between phase currents and line currents and show you that for the Y-connected load, those things are equal, right? IA is equal to the current in this load, where IA here splits between two loads. And so when we go and do the math to try and determine this current here, we need to take that into account. Ultimately, all we really need to know is that as long as I take the correct voltage, which in this case would be VAB, I can still know that the current here is going to be VAB over ZC, right? Not very difficult. Same old stuff. We're still just using Ohm's law. The circuits just look a little bit different because now we have three phases all going on at the same time. It's all the same stuff. All right, so I'm going to go ahead and end this video. I think that this wraps up this section of the module. Yep. And in the next section, we're going to show the possible three-phase configurations, and then we will solve some example problems. And then we'll be pretty close to wrapping up this module, which is super exciting. All right, so I'm going to go ahead and end this video here.